Hi guys, I'm Saurya and I'm going to explain about quicksort algorithm. Hi guys, I'm Saurya and I'm going to explain about quicksort algorithm.
Quicksort. It is an efficient divide and conquer algorithm. Quicksort stands as a pinnacle of efficient sorting algorithms, embodying the divide and conquer paradigm with elegance and power. This algorithm has become a cornerstone in computer science, which is widely used in various applications due to its exceptional average case performance. Quicksort's ability to efficiently handle large datasets makes it a go-to choice for many software systems, from database management to graphics rendering. In its place, sorting capability, adaptability to different data types further cement its status as a versatile and indispensable tool in a programmer's arsenal. What is Quicksort? Quicksort mainly embodies four main principles: divide and conquer strategy, pivot based partitioning, in place sorting, average case efficiency. In divide and conquer strategy, Quicksort employs a divide and conquer approach, breaking down the sorting problem into smaller, more manageable subproblems. This strategy allows for efficient handling of large datasets by recursively dividing the array into smaller portions. Pivot-based partitioning. The algorithm selects a pivot element from the array and partitions the other elements into two subarrays, according to whether they are less or more than greater than the pivot element. This process is then recursively applied to the subarrays. In-place sorting. One of the quicksort's distinguishing feature is that its ability to sort the array in place, meaning it doesn't require additional memory proportional to the array size, making this memory efficient and suitable for large datasets. Average case efficiency. Quicksort boasts an average time complexity of order of n log n, making it one of the fastest sorting algorithms available. Its efficiency in practice often surpasses the other algorithms with the same time complexity. Key principles of quicksort: pivot selection, partitioning, and recursion. Pivot selection. The choice of pivot element is crucial for quicksort's efficiency. Common strategies include selecting the first, last, or the middle element of the array, or using more sophisticated methods like the median of the pre-approach. A good pivot selection can significantly impact the algorithm's performance. The partitioning step is the heart of the quicksort. It rearranges the array so that all the elements smaller than the pivot are moved to its left, and all the large elements to its right. This process creates two subarrays that can be independently sorted, leveraging the divide and conquer approach. Recursion. Quicksort applies the sorting process recursively to the subarrays created by partitioning. This recursive nature allows the algorithm to efficiently handle arrays of any size, breaking down into smaller and more manageable pieces until the entire array is sorted. Step-by-step walkthrough with HGLs. Now we will go through how we can perform quicksort to an array. Initially, let the array be 64, 34, 25, 12, 22, and 90. Now we choose the pivot element. Let's say in this case it's 90. Now we partition the array into smaller pieces such that the smaller elements than the 90 are onto the left and greater than 90 are onto the right. Now we recursively apply quicksort to the left subarray and the right sub. Now we finally group together sorter arrays, resulting in a fully sorted array. In the pivot element. If the first element is chosen as the pivot element, it can lead to poor performance on an already sorted or a reverse sorted arrays. It's vulnerable to the worst case scenario of order of n squared. Last element. Using the last element as the pivot also is also straightforward and works well in many cases. However, like the first element approach, it can perform poorly on sorted or reverse sorted arrays. Random element. Choosing a random element as the pivot can help avoid worst case scenarios and provide good average case performance. This method also adds a level of unpredictability that can be beneficial for handling various input distributions. Median of three. This method selects median of first, middle, and the last element as the pivot. It often provides better performance by reducing the chances of a poor pivot, especially for partially sorted arrays. Partitioning the array. We partition the array in four main steps: initializing the pointers, compare and swap, placing the pivot, and returning the partition checks. Initializing the pointers. Two set pointers, let namely them be I and j at the start and end of the array respectively. The I pointer will track the element smaller than the pivot when the j moves through the array. Comparing and swapping. Move j from left to right when the element smaller then the pivot is found. We increment I and then swap it with I and j. This process ensures that all the elements smaller than the pivot are moved to the left of the array, placing the pivot. After j reaches the end, we swap the pivot with the position of I plus 1. This places the pivot in its correct sorted position with all small elements to its left and large elements to its right, returning the partition index. The index where the pivot is placed becomes the partition index, which is used to divide the array into two subarrays for further sorting and recursive steps of the algorithm. Recursive sorting of the subarrays. We have initial call, left subarray, right subarray, and base case and combining results in this case. Initial call. The quicksort function is initialized on the entire array. This serves as the root of the recursive tree, setting stage for dividing the problem into smaller subproblems. Left subarray. After partitioning the quicksort is recursively called onto the left subarray. This continues further, dividing the left sub into subarrays, becoming trivially small until the elements become zero or not. Right subarray. Similarly, the quicksort is recursively applied to the right subarray, namely containing the elements larger than the pivot. This ensures that all the elements to the right of the pivot are sorted through successive partitioning and recursive calls. Base case. This recursion stops when the subarray has 0 or 1 elements and are inherently sorted. This base case is crucial for terminating the recursive process and preventing infinite recursion. Now we combine the results. As a recursive cause return, the subarrays are implicitly combined. Since each partitioning step takes place the pivot in its correct position and no explicit merging steps is required, unlike in merge sort. Now we are into time complexity of quicksort algorithm. In the best case, we have order of n log n, which is in the scenario of balanced partitions. Average case, it has an time complexity of order of n log n with the scenario of random input. Worst case, we have worst case in the case of order of n square in the scenario where the array is already sorted or in a reverse sorted manner. Quicksort's time complexity varies depending on the input and the pivot selection. The best and the average cases, it achieves an order of n log n complexity, making it highly efficient for large datasets. The best case occurs when the pivot element always divides the array into equal halves, resulting in a balanced recursion tree. Average case of n log n is achieved for random input distributions where the partitioning is reasonably balanced over the course of the algorithm. However, in the worst case, when the input is already sorted, a reverse sorted, and the pivot is always chosen as the first or the last element, the complexity decays to order of n square. This occurs because each partitioning only reduces the problem size by 1, leading to n recursive calls. Space complexity and in-place implementation. In-place sorting. Quicksort is an in-place sorting algorithm, meaning it doesn't require additional memory proportional to the input size. This makes it memory efficient and suitable for sorting large datasets where memory constraints are a concern. Recursive stack. The space complexity is primarily determined by recursion stack in the average case. The stack depth is order of log n, resulting in an order of log n space complexity. However, in the worst case, the stack depth can reach order of n, leading to an order of n space complexity. Optimization techniques. Various optimization techniques can be employed to reduce space coefficients, such as tail recursion elimination, iterative implementations. These can help maintain the algorithm's efficiency while minimizing the memory overhead. Now we are into applications and use cases of Quicksort. Standard libraries use Quicksort. Database systems also use Quicksort. Also, numerical computations and information retrieval also use Quicksort. In standard libraries, Quicksort is widely used in standard libraries implementations of sorting algorithms in various programming languages such as C++. In Java, it is also used in Java's arrays.sort or a hybrid algorithm that also includes Quicksort for primitive types. In database management systems, they employ Quicksort for efficient data retrieval and indexing. Its ability to handle large datasets makes it particularly useful for sorting database records and optimizing query performance. In numerical computations, scientific and numerical analysis, it is mainly used to sort large arrays of numerical data. Its efficiency in handling large datasets makes it suitable for applications in physical simulations and financial modeling. In information retrieval, search engines and information retrieval systems always use Quicksort to efficiently sort the rank search results. Its ability to handle diverse data types makes it versatile for sorting text, numerical scores, or complex data sets. Thank you.